SwayamPrabha. Digital India. Educated India.
Hello everyone, this is the fourth lecture of this week, and today and the next lecture we'll be writing a computer program for finite element method applied to two-dimensional elasticity problem. By now we already know what are the element level equations, finite element equations for elasticity problem. We know how to compute the stiffness matrix, then load vector, traction vector. We also know the isoparametric formulation. So let us put all the understanding we have so far, let us put them in one basket and then see how these can be translated into a computer program through which we can obtain solution, finite element solution for general class of problems. Okay, two-dimensional elasticity. Now, to start with, let us quickly revisit the equations that we'll be using. We are familiar with these equations. This is the element level equations. This is element stiffness matrix, element nodal degrees of freedom at the element level. This is the body force term. This is the traction term. And this is how the stiffness matrix can be computed. Where B involved requires the derivative of the shape functions. C is the constitutive matrix. For plane stress, it is like this, and for plane strain, it is this. Body force term can be obtained by this, where Fx and Fy are the component of body force term in x and y direction. To compute the traction term, we need to do a boundary integral, and this integration needs to be performed only on the boundary of the element which coincide with the traction boundary. Now, just to put all the equation in the context of a triangular element, constant strain triangular element. For this, we know that our shape function, derivative of shape function is constant over the element, and therefore B matrix will be constant. And so if C is constant over an element, and then the entire stiffness matrix for an element will be constant. So in order to get the stiffness matrix for a triangular element, we do not have to explicitly integrate it. And Te is the thickness of the element. Now, we also know for a triangular element, body force term required this integration of the shape functions, and we know for a triangular element, this element, integration of the shape function gives you A by 3, and therefore body force, the vector corresponding to body force term will be like this. Now, this is the traction vector. As I said, this needs to be evaluated on the boundary of the element which coincide with the natural boundary of the domain. For instance, if we have some tractions prescribed on this boundary, suppose this is the boundary on which some traction is prescribed, then this integration needs to be performed only on this boundary, right? So this integration, if we write integration of boundary 1 2, then plus integration boundary 2 3, gamma 2 3, and then plus integration gamma 3 1. So we do not have to perform this integration for boundary 1 2 and for boundary 1 3. So we don't have to do this. We do not have to do this. Only this boundary, the integration needs to be performed. Now, how to perform this integration? If you remember, we had discussed, depending on the numbering, we need to construct a local coordinate system. For instance, this is the node number is 1 2 3. So local coordinate system will be something like this. This is S, and this is the origin of S, and on this we need to integrate. So this is your 2, and this becomes 3, and this is our local coordinate, and on this traction is prescribed, right? And this is the unit normal, outward normal, here unit outward normal become this. So on this we can evaluate this integration, and then using the transformation matrix we know what is the angle, what is the orientation of this line. Using the transformation matrix we can obtain the traction term, right? So now let us start with, before we write the program, let us first start with revisit the examples that you have already taken in last week. You recall this was the example. You have done the manual calculations and obtained the solution of this problem using two finite elements. You have discretized the entire domain like this, and with these two elements, this is the solution we have obtained. Now there are two important parts in this solution. Okay. First is, of course, we have just taken two elements, therefore we really do not know whether this results that we obtain, whether it is closer to the true solution or not, or it is the converged result or not. For that we need to increase the number of elements and then see how the response converges to the true solution. That exercise we have to do. But another interesting observation is, you look at the problem. This problem is symmetric. If we, in terms of the geometry of the domain, in terms of the loading conditions, this problem is symmetric with respect to this axis, right? Now, if the problem is symmetric, means loading is symmetric, geometry is symmetric, then it is expected the response also to be symmetric. But if you look at the solution, now for this problem, U1, V1 will be at this point, this is the boundary, these two are the boundary point, therefore U1, V1 and U3, V3 are 0. These are the boundary condition we need to impose after we have the global stiffness matrix, and then when we solve this condensed equations, we get these solutions. Now look at this solution, U2, now our intuition says, see whether the solution is right or wrong, whether it is a converged solution or not, those things we need to check by increasing the number of elements and then see the solution. But before we do that exercise, let us apply our intuition. Our intuition says, just now as I said, because the problem is symmetric, this response is also expected to be symmetric. But when you look at the response, it is not so. For instance, our intuition says that U2 should be equal to U4, but U2 here is 11.28 and U4 is 10.10, which is not same. Again, V2, our intuition says that V2 should be equal to minus V4. If V2 in this direction, V4 will be in this direction. So V2 is 1.9697 and V4 is 1.09, minus 1.0. Then nature is fine, one is plus, another one is minus, but the magnitude is not same. Now this is an interesting, this observation is interesting because you see now we have just two elements only now, and the domain is also very simple. Now we may have to eventually we will be applying finite element method for a very complicated geometry, having large number of elements we'll be having, then we get a solution. Solution means we'll get a number, right? But that it is very important to check all the numbers that we obtained by solving some equations. Those numbers carry some meaningful information about the problem, whether those numbers represent the physics of the problem properly. At least the numbers we have on our screen right now, whether these numbers is correct or wrong, those things, before we check that, just by intuition we can say the numbers that we have obtained by solving some equations, these numbers do not represent the problem properly. At least the nature of these numbers do not represent, they do not go in line with the problem, the loading conditions, the geometry. Okay, but now but then the question comes, is it that always we argued that time that because our element is not symmetric, that's why we have not obtained the solution is not symmetric, which is justified because we can see that here you have element number 1 and element number 2, node number 4, we will get contribution from these two nodes and these two elements. For node number 1 only contribution, node number 2 only contribution from element number 1. So this is justified. That's because we do not have symmetry in the discretization, we are not getting response which is supposed to be symmetric. But the question is, if it is a very simple domain, but if the symmetric discretization is a requirement, then it is absolutely not possible for most of the structure, because when we discretize a structure, complicated geometry, then it is not feasible to maintain that symmetry in the discretization. But then these discrepancy must go as we increase the number of elements. This should happen. If that doesn't happen, then there is a problem. For 2 elements, I understand the results we have obtained, that results there are discrepancies, but as we keep on increasing the number of elements, 2 things must happen. One is it should converge to the true solution, and this discrepancy also must go. That exercise also we will do and check, right? So let us start writing the code. Code is written as the practice we have been following. I will go through the entire code, and then we'll take up some example and get the solution. So this is a 2D elasticity problem using FEM. So the first one is the physical domain. So we have to define what is the domain we have, and then let's start with this code. This is the physical domain, and hx and hy. Hx is the element size of the element in x direction. Now size of the element means hx is the divisions we want in x direction, and hy is the divisions we want in y direction. Okay. So for this problem we have taken hx is equal to hy, but we can change it. Now these are the properties, Young's modulus, and then we have Poisson's ratio, then thickness of the element. Then this is the constitutive matrix. This is for plane stress condition, and this is for plane strain condition. Okay. Now F body it tells you what is the body force term in x direction and body force term in y direction, and Tn is the traction term. Means for this example, if you take our traction term is this. So x direction it is 10. That's why it is taken as 10. Now, so this is our traction term. Next is the discretization of the entire domain. The discretization part is same. We have already discussed this part while during heat conduction problem. Now this is the element connectivity, and this is the plotting of the discretization. We will plot and see. Now next is identifying the nodes on essential and natural boundaries, right? Now for this problem, you look at our essential boundaries this is our essential boundary, means that x is equal to 0 is the essential boundary, and natural boundary is x is equal to 120. So this is EBC is the essential boundary condition, x is equal to 0, and NBC natural boundary condition is x is equal to 120. So find is a command in Scilab we had discussed earlier. So what this command, this function does is it identifies the nodes for which x is equal to 0 and store that indices of those nodes in EBC. So essentially EBC will contain the nodes, the IDs of the nodes on which the essential boundary condition to be imposed, and similarly NBC will be the set of nodes on which the natural boundary conditions to be imposed. Then the next is the initialization of various matrices. Now here at every node we have 2 degrees of freedom, ux and uy. So the size of the stiffness matrix will be 2n by 2n. In this case, n underscore node is the total number of nodes we have in the system. Similarly, for body force term will be 2n by 1, and then traction term will also be 2n by 1. Now, once this is done, next thing is computation of stiffness matrix and the load vector. So idea is we'll Now we will take individual element, write the stiffness matrix, element stiffness matrix, or rather the element equations for that particular element, and then based on the connectivity we will populate the global equation. Okay, so first is the KE. So this loop is over the entire element. En underscore EL is the number of element we have. K is the size of the stiffness matrix, element stiffness matrix, and FE and QV are the element level body force term and the element level traction term. I1, I2, I3 are the global node number for that particular element. For instance, for nth element, this gives you the local node number, element level node numbering of nth element 1, 2, 3, and I1, I2, I3 are the corresponding global node number of then x, c, y are the coordinates of these nodes. Jacobian, J is the Jacobian, and Jacobian is constant for this element. We have already seen this is the constant Jacobian, and then once we have the Jacobian, this is not Jacobian, but Jacobian we require to get the area of this triangle. We had discussed how to compute Jacobian, and once we can compute the Jacobian, we get the area, and then finally we get B, and then K, stiffness matrix is constant. So this gives the Jacobian, and area will give you this determinant, half of determinant of Jacobian. This is B matrix, which is constant, and once we have the B matrix, our stiffness matrix will be this B transpose dB. A is the area and multiplied by the thickness of the element. And similarly, FE will be this. This FE will be AE by A into T by 3 into this body force term in x and y direction, and this will be the AE by AT by 3 into body force term in x and y direction. Now, so once we have this, we have computed the element stiffness matrix and element body force term. Next is the globalization of the stiffness matrix. We will come to the traction vector. Next is the globalization of the stiffness matrix. The globalization, how to do? For element stiffness matrix, we know the global node number, and based on the global node number, we populate the global stiffness matrix, right? And this is done here. So this 1, 2 is the element level node number, and corresponding 1 toward the element level degrees of freedom, and the corresponding degrees of freedom in the global level will be this, right? Similarly, 5, 6 is the element level degrees of freedom, and corresponding degrees of freedom in the global level is this. So this is how the this global stiffness matrix is obtained. Now, similar logic we can use for body force term. This is the element level component, and then corresponding global component will be this. Now, next is the boundary traction term. Now, we have 3 boundaries. Just now we discussed boundaries, that boundary integral need to be performed on. Now 3 boundaries we have on the element. Now, boundary number, boundary 1, 2, then 2, 3 and 3, 1. So, gamma 1, 2, gamma 2, 3, gamma 3, 1 are those boundaries, right? And then, now we need to search whether on that particular boundary traction is prescribed or not. If traction is prescribed, then only this boundary integral term is to be evaluated. Otherwise, not required. That evaluation is not required. So, this is that checking. So, this gives you the length of that boundary. And then, now what this does is, we have already stored all the nodes on which essential natural boundary condition to be prescribed in NBC, right? So, what it will do is it will search over NBC and see and check whether for the given element, what are the node numbers we have, whether that node numbers belong to this set or not. If that belongs to this set, that pair is belong to that, both the nodes number of a boundary belong to this set, then on that boundary, naturally the traction needs to be prescribed. For instance, gamma 1, 2 means it will check whether global node number I1 and global node number I2, whether these 2 nodes belong to NBC or not. If both the nodes belong to NBC, it means that on this boundary, natural boundary condition to be specified. Similarly, gamma 3, 1 means I3 and I1 are the global node number. It will check whether both the nodes belong to NBC or not. If it doesn't, then not required, and if both the nodes belong to this NBC, then boundary condition, natural boundary condition need to be specified. How to know that? Now, if none of the nodes I1, I2 or I2, I3 or I3, I1, none of the nodes belong to NBC, then our the value will be, it will be a null set. Gamma 1, 2, if both the nodes I1 and I2, none of them belong to NBC, then result will be a null set. If only one node belong to NBC, then gamma 1, 2 will be just carry one value. Which node? The node which belongs to NBC. But even in that case, no boundary condition need to be specified. If both the nodes belong to NBC, then size of the gamma 1, 2 will be 2, length will be 2, and then that the gamma 1, 2 will carry. If length of gamma 1, 2 will be 2, means that the natural boundary condition need to be specified. So it is an indirect way of identifying whether natural boundary condition to be prescribed on this boundary or not. But this is not the indirect way, and I would say a crude way, because this idea of this program is not to, as I said at the very beginning of one of the weeks where we started writing program, the idea here is not to write a finite element, write a very efficient finite element code. The idea here is whatever we have learned, let us translate them into a program so that we can handle larger problem. Okay, so next is the traction. Once we know this, compute the QE. If we know that on this boundary natural boundary condition to be specified, so these are the traction vector at the element level. Again, this code is specifically when traction vector is uniformly distributed on the boundary. But if it is linearly varying distribution or other distribution, we have to modify this code accordingly. All the code will be uploaded on the forum, and that generalization I leave it to you. So once we have the element level traction vector, next is the globalization of that traction vector. The logic is exactly same, depending on the local element level node number and what is the corresponding global node number. This we can populate the global queue. So once we have then all these load vectors and stiffness batting, next is the partitioning of the matrix based on the known and unknown information, and once that is done, the next is the solution of the condensed equations. And if we solve the condensed equation, this is the solution of the condensed equation, and then backslash is the solving the linear equation. Okay. Now then once we have the solution, then the globalization of these degrees of freedom, and next part is the post-processing, deformed shape and the contour plot of the primary variable. Then we can compute the stresses as well. We have already discussed how to compute the flask term. Similar way we can calculate the stress. Okay, stresses at the gross points. Now once this code is, we have written the code, the first thing is, for any code you write, the first thing is the validation of the code. Before we apply this code to other problem which having general boundaries and more number of elements, let us validate it. And how to validate it? We have already result of this problem, right? We have done the manual calculation, result of this problem. So let us let us take two elements only, and then run the program, get the solution. Our solution from the code should be this. Okay, so let us do that. So let us take h is equal to 2. H is equal to 2 means in parametric space your size of the element will be 2. So let us run it. Yes. So this is the contour plot of which displacement is plotted. This is ux is plotted. Yeah, this is ux is plotted. Okay, so this is the plot of ux, and this is our deformed shape. Black one is the undeformed configuration and red one is the deformed configuration. Now we have already identified these nodes. Okay, so let us check the u of id, and let us multiply it by 10 to the minus 4. So let us multiply it by 10 to the 4. So this is our result. Okay, so let us compare this. We have 11.28 and 1.97 at node number 2. It is 11.27 and 1.97 at node number 2. and next is 10.1 and minus 1.09, 10.1 and minus 1.08. So this result is fairly matching with our manual calculation. So at least we are sure that all the calculations and assembling we are doing in the code, that is working. Okay. Now next what we'll do is we'll increase the number of element and then see at what value the result converges, and as we increase the number of element, this discrepancy which is contradictory which with our intuition whether that goes or not. Okay. So close it. So let us make it one element, refine it. So this will be our element, this will be our results. So this result, this is 11.37, this is 10.58, 1.39, still it is there. Let us further increase the number of element, and then check. So it is discrepancy is still there, this one and this one, and then still you increase the number of element again, and then this is becoming closer. This is 11.2, just taking the first decimal place, 11.2, and the 11.1 it is 2.01, and this is 1.9. So let us further reduce it. Let us make it 1 to 5, 1 to 5. Okay, and then check. So this is 11 point. It is better. 11.1, 11.2. This is also 11.2. So at least these values, which was 11.28 and 10.1 with just two elements, now it is symmetric. And this is 2.01. It is 1.96, which is also almost 2.0. So if you further reduce the size of the element, you will get you can see what happens. So that exercise I leave it to you. Okay. Now, so this was one problem, and let us take one more example. This is another example. This example is if you this is the elasticity solution. This is the elasticity solution. Okay, the solution is at this point. If we take a point like this, which is 0 and 1, 0 and 1. And the displacement will be something like this. Okay. So we will see our finite element solution, where our finite element solution stand vis-a-vis this elasticity solution. Okay. So let us take this example. So this is the boundary defined, and then natural boundary, essential boundary conditions and natural boundary conditions are defined on this domain. We have so body force is 0, 0, and then traction is given as 150 into T. T is the thickness, so 150 is tau. This tau is 150. So T is the P is the one total force will be tau into 1 into thickness, and then the boundary conditions are this: essential boundary at x is equal to 10. We have essential boundary at this. We have essential boundaries, and natural boundary conditions is at x is equal to 0. Rest of the things we don't have to give. These are the properties, and this is plane stress condition. So this is the D matrix. So let us start with first level discretization, and we know that our elasticity solution gives you this. So this is our first level discretization. This is the plot of probably it is a plot of Ux, and this is the discretization. And what is the value? Your value is around minus 1560. Okay. So let us write this value. So this is minus this is minus 0.156. Okay, I am taking only this thing, our y component of the displacement, and that is multiplied by 100. Okay, now let us further increase the number of element. So this is our next level of discretization, and it will give you u is equal to minus 0.321, minus 0.321. This is minus 0.321. These are all multiplied by 100. Okay, and the next level discretization, if we take 125, okay, so this is our solution is minus 0.445, minus 0.445. So here it is 0.5 discretization, 0.25. This is 0.125. Let us further divide, do that exercise. Now the plot, if we comment, then it won't take much time. Okay. Okay. Let us further divide it. Let us make it 0.625. Yeah, this is the plot. Then u will be 0.494. So we have 0.0625. This is 0.494. Our elasticity solution is we have 0.502. 0.502. So 0.502. So you see, we have started with 0.5 discretization. The value is this, and as we go on, keep on increasing the number of elements, and eventually if you further take it, if you one level of refinement will give you probably much closer to this value, which is this is already very close. So this is how we can now after that, after some time, we will see that even if we increase the number of elements, the changes are very small. For instance, from this to this, changes is significant, it is almost double, but then from this to this, significant, it is the rate of the change is now less. Now again from this to this, which is very small, if you one level of refinement, you will see that it will hardly have any change. So when you see that the even after increasing the number of elements, the changes in the solution is very minimum, very small within the tolerance level, we can assume that this is the converged result. Okay, now let us stop here today. So next class we will again take similar examples but with different elements, quadrilateral elements, for which we need isoparametric formulation. Here for triangular element, without isoparametric formulation we could do, but then with quadrilateral elements we have to use isoparametric formulation. That we will discuss in the next class. Thank you. See you in the next class.